discussing about different possibilities of branch prediction in order to increase the available parallelism in a system or reduce pipeline stalls that can happen due to control hazards, that is branch hazards. So, we are discussing about these 1-bit branch predictors, and we have thought that okay, that can be generalized, right. I can have a 2-bit branch predictor, essentially a branch predictor which will try to predict a branch decision based on more amount of branch history. So, all that a 1-bit predictor does is it just looks at the previous decision and repeats it. A 2-bit branch predictor looks at the last 2 decisions and tries to do something like that, right. So, this is an example of a branch predictor designed with a 2-bit saturating counter. So, I mean just to motivate why this is a good thing, first of all we have already understood earlier that there are 4 states: strongly not taken, weakly not taken, weakly taken and strongly taken state. So, strongly taken means I am always deciding to take the branch, and this we have already discussed. If once I go wrong in my decision, I come to weakly taken state. Here also I want to again take the branch. Again if I go wrong in my decision, I come to weakly not taken state. Here I am always predicting that I will not take a branch. If I am correct, that means a branch is really not to be taken, then I go to the strongly not taken state, where also my decision always is to not take the branch, and I shift from strongly not taken to weakly not taken if I go wrong once, that is the branch is taken. I shift from weakly not taken to weakly taken if I go wrong again, that means I predict that the branch is not taken, but it is again taken, and so on and so forth. So, just to observe the performance of this system, let us go back and think of the performance of a 1-bit branch predictor in a worst case scenario. So, a worst case scenario would be something like, suppose I have a program which is executing with a sequence of, I mean the actual branching decisions denoted by 1s and 0s are like this, they are going to be alterations. So, let us say I am executing a loop inside which there are 2 branches. It is always the case that the first branch is taken and the second branch is not taken. So, that gives me this pattern. How do you think that the 1-bit branch predictor will work? So, let us say its initially is in the taken state. So, it will predict this correctly, and then it will think that okay, in the next branch also I should take the branch. So, this will go wrong. Now, it sees that it has gone wrong. So, in the next state it again wants to not take the branch, whereas the real thing is that the branch has to be taken. So, it will go wrong and the behavior will continue, right. So, you are always predicting wrong. How about using this 2-bit branch predictor here? I mean, of course, the behavior will depend on my initial state. Let us assume that I am in the strongly taken state. Okay. So, assuming that, let me again write this sequence here. So, I am in the strongly taken state, that means this one I predict that I will take and I am correct. Then here again I am in the strongly taken state, but the real branch is not supposed to be taken. So, I go wrong because I am always thinking I will take it. So, then I will also have a state change, right. So, assuming that in the automaton you see that I am now going to switch from this strongly taken state to the weakly taken state, because although I thought that the branch is taken, it is really not taken, but still my decision is, since it is a weakly taken state, for the next branch I am again going to take the branch, right. So, I will go correct here. So, then that would also mean that I switch, since the branch is really taken, I switch to the strongly taken state, right. So, again for the next prediction it will go wrong, and then again I go correct and I go wrong, like that. So, I have an improvement in performance here over a 1-bit saturating counter. So, in that way I can see that with addition of some history of information, I get an improvement in performance. Now, of course, I can keep on making a more complex branch predictor by looking into more amount of history and taking suitable logical decisions, or alternately I can make the branch predictor even smarter and go for what we known as a hierarchical predictor. So, if we generalize the idea, it would be something like this, that we look into branch histories and take decisions. Now, suppose I am always looking at an m length history. So, there are 2 to the power m possible branch histories. So, I store this different this history in a location, maybe a shift register, and so I have 2 to the power m possible values of this history, and for each of these situations, that means for each of these 2 to the power n possibilities, I have one n bit predictor. So, just to understand back, here what we are doing, we are looking at the last decision and doing a prediction. So, the prediction decision is based on 2 bits, right. It is a 2 bit saturating counter decision, but I am looking at the last decision, right. So, I can also do is I can look at the history of m length, and for each possible such sequence I will take the decision based on another n bit predictor. So, this is a combinational scheme. I have a hierarchy. First I see what is the branch history, and then I look at for this history, for this specific history, what is the state of my n bit predictor among those weakly taken, strongly taken, less weakly taken, more strongly taken, because there will be more tests, because if n is greater than 2 and all that. So, I mean, in that way I can take a more informed decision. It is known that if I have a 2 level predictor with an m bit history, it can predict any repetitive sequence with any period if all the m bit subsequences are different. Let us understand what it means. Suppose I am doing a 2 level predictor, and my choice of m means I am always deciding based on an m bit history. Now, it can predict any sequence which will repeat with some period if all the corresponding subsequences, these m bit subsequences are different. That means, for the m bit subsequence, the decision is always unique. So, that was a bit of divulging into the idea of branch predictors and looking into some amount of their intricacies, if not all, and we are also not getting into the details, because in general hierarchical prediction is a very complex phenomenon. There are a lot of other predictors like tournament predictors. You can just go into those details if you are interested from an advanced architecture point of view. Now, the next important topic here for us is the issue of dynamic scheduling for instruction level parallelism. So, what is that? Now, we know that simple pipelines execute instructions in order, like I have this sequence of instructions, divide for double type, add, sub and all that. Now, look at the operands here, from which it is very easy to decipher that the subtract instruction will suffer unnecessarily as the add instruction gets stalled due to dependence. So, what is that? The div instruction is going to write to F0. Now, this is again the read operand for add. So, this is something we have already discussed earlier. It is a read after write dependency, due to which add will stall. Now, sub has no dependency on add. I mean, it's basically reading, the only common thing is F8, but it's a read after read. So, there is not any kind of hazard or stall that's going to happen. So, there is practically no reason why sub should suffer due to add getting stalled with the preceding instruction div. However, observe that if I do an alteration here in the ordering, I can avoid the stall, because I can just execute, because add will get stalled here, I can just execute sub before add, then there is no stall. Now, this is the good thing for this specific case, because sub has no dependency, and observe that I can have a recognizer system in the hardware which can actually identify that yes, there is no dependency and this can go before this, right. So, I can have this kind of modified I can have this kind of reordering of instructions, that is executing instructions out of order to get more instruction level parallelism and increase the effective CPI, right. However, there are issues. I cannot do it in an ad hoc way. In this case, it is good, but if we just think of the earlier issues, like as we discussed the hazards of type WAR or WAW, those can come in if I am doing out of order execution. So, I have to be very careful here that when I am executing out of order, I should choose the order in such a way that these possibilities of WAW and WAR type hazards do not creep in. In this way, there is a very famous algorithm by Robert Tomasulo, well known as Robert Tomasulo's algorithm, which is basically a way of choosing instructions that would execute out of order while minimizing these WAW and WAR type hazards and resulting stalls. So, essentially the algorithm will track when operands for instructions are available to minimize this hazard, and they actually employ some optimization techniques well known as register renaming to minimize this kind of hazards. So, let us look at an example of this register renaming. We are not, I mean, just to be very clear, we are not getting into Tomasulo's algorithm. There is quite a lot of stuff to be covered right now. For our purpose, it is not also necessary. Discussing about the register renaming option. So, if you look to the code in the right hand side, as you can see, we have introduced two new register options S and T, and and there is some significant modification that has been done into the original code of the left hand side. The modification is as follows: the add instruction, which is the second instruction, earlier it was writing to the register F6, now it is writing to another register S, and similarly F6 has also been replaced by S in the next instruction, that is the store instruction, and in the sub instruction which was writing in the register F8, this is being removed, and there is a new register T in which it is writing, and similarly in the subsequent instruction mul also F8 has been replaced by T. So, this helps in removing several of the possible hazards that can come in. So, let us look into the issues that get solved by doing this register renaming operation. So, as you can see, this inclusion of this register S removes the read after write dependency of the multiply instruction. Now, where is that read after write dependency? So, this multiply instruction was reading from F8, whereas and F10, and it was writing to F6, right. It was writing to F6. Now, what is happening is this read after write was dependent essentially on this F6, this S, this store instruction. Now, let us explain that once again. So, as we can see, this multiply instruction is writing to F6, whereas the store instruction is reading from F6. Now, this is a read after write, which would mean the store instruction cannot be executing after the multiply. There cannot be any ordering, I mean reordering possible between multiply and store. But now, once I make them independent, that is this S is being used here instead of F6 for the store instruction. That means there is no read after write, write after read dependency between the multiply and the store instruction. So, now the store instruction is reading from the register S and writing to the location in R1, whereas the multiply instruction is writing to F6. So, now there can be an instruction reordering between this store and this multiply. So, in that way this new register S removes this write after read dependency of multiply on the store instruction. So, essentially this issue gets resolved as I am pointing it out here, this issue of write after read is getting resolved. Now, there are some more similar issues that are getting resolved. For example, there was a write after write issue also, that is, as we can see that F6 is being written by multiply and F6 is also being written by add. So, earlier there was a strict ordering that add should happen before multiply, but since now that is also being changing, right, because add is writing to S and multiply is writing to F6. So, they are different registers. So, in that way this register renaming of S removes the write after write dependency of multiply also. Now, what else is getting resolved? Let us see, because we have also included some other register which is the T register. So, earlier there was this write after read dependency of the sub instruction. So, it was writing to F8 and F8, this subtraction instruction was writing to F8 and F8 was read from by the add instruction. So, again there was no reordering possible between add and sub, but now since sub starts writing to T, there is a possibility of reordering between add and subtraction instruction. So, in that way this register renaming by T removes the, so in that way this register removing renaming of T removes this write after read dependency of sub, because it was writing here to F8 and addition was happening from F8 also, but now addition is reading from F8, but sub is writing to T. So, they can be ordered differently. So, in that way several of these dependencies gets removed with this register renaming operations, and that creates a case for suitable reordering of instructions, which can help in increasing the effective parallelism if there is a possibility of executing multiple instructions in multiple pipelines in parallel. So, we are just trying to show that these are the possibilities here. This example has been also taken from the classic book by Hennessy Patterson, similar to most of the other examples we discussed in this introductory slide, and we are just trying to point out that with this kind of optimizations, they can be easily be carried out by compilers, and once they are done, they really help in exploiting more amount of parallelism. So, as we have discussed earlier, that there can be several possible ways to do this kind of optimizations. They can be done with hardware support as well as software support. By software support, we mean a smart compiler can do this kind of operations. By operations I mean deciding which instructions are going to be issued in parallel or not. Also, a smart hardware can do the same. Now, it depends on you. We like to tackle this problem of deciding independence of instructions at which level, at the compiler level or the processor level. Now, of course, whatever can be done at each level is also different. Just to take a case, like when I am trying to do some optimization by the compiler is not aware of the arguments that are provided to the program. So, all that it will do is some static optimization by looking at the program. More or less whatever we have discussed is all static optimization, because we are not using any concept of dynamic optimization, which is based on what is the value in the register. We are just looking at the dependencies and the hazards. So, these are all static optimizations which can be done by a compiler or can be done by a smart hardware. So, depending on where you want to do this, there can be several different possible processor design styles. So, when processor design styles, when we are looking into the issue of how I can resolve dependencies among instructions and issue multiple instructions to be executed in parallel. So, based on this classification, we have the following three possibilities here. The first one is VLUE style of execution. VLUE stands for very large instruction word. So, this is a style of microarchitecture design where the effective parallelism is exploited by the compiler. So, the compiler decides which are the instructions that should execute in parallel, and so essentially the compiler schedules these instructions and their parallel execution, issues a fixed number of instructions formatted as one large instruction. So, essentially the compiler will look at the actual instruction stream and come up with packets of large instructions, and each packet kind of stitches together a set of independent instructions which can be executed in parallel, and that is fed to multiple independent functional units so that they can execute in parallel. So, here this is a more of a compiler intensive approach. The parallelism is decided by the compiler, the hardware is blindly following it and executing the instructions in parallel using multiple functional units which are already present there in the VLUE style of architecture. Now, as example, there are well known processors which do digital signal processing, which are designed based on this philosophy. So, apart from this VLUE style of processors, we also have the other two options, which is statically scheduled superscalar and dynamically scheduled superscalar. So, by statically scheduled we mean that the compiler decides which are the instructions that are to be issued in parallel. However, the execution of these instructions are in order. So, we have pipelines executing the instructions in parallel, but the compiler still decides which are the instructions that will be issued. The instruction issue width may vary. Coming to the last option, which is dynamically scheduled superscalar, here the hardware decides instead of the compiler that which are the instructions that are going to be issued in parallel. Also, the other important thing is the hardware executes these instructions out of order. Now, if the design philosophy is that we should have a very large issue width, then VLUE is preferred with respect to statically scheduled superscalar, simply for the reason that both approaches require support from the compiler, and if we are really deciding that the compiler should be packetizing or doing the issuing of parallel instructions, the VLUE makes sense because of the large issue width, because if we are keeping large issue width, but still doing statically scheduled superscalar, then the problem is the number of instructions that will be issued may vary. Now, when this varies and it is not always accompanied, I mean filling up this large issue width, then it does not make much sense to have a large issue width. So, typically this idea of statically scheduled superscalar is used for narrow issue widths, maybe 2, but for large issue width VLUE is the preferred way to design, but most popularly used for most of the microarchitectures, the design that is followed is dynamically scheduled superscalar. So, in short summary, these are the different architectural styles that are practically employed for deciding how to exploit the parallelism resident inside instructions and execute more number of instructions per clock cycle. And over this lecture, we have tried to summarize the topics like how a basic RISC pipeline operates, how the memory is organized along with this basic RISC pipeline, what are the limiting factors with respect to instruction execution in the pipeline, and to alleviate those limiting factors, what are the optimizations that can be done. So, that would be our overall review of existing computer architecture notions that we will be using for building upon them for the GPU architectures and programming part. So, with this we will conclude this topic, which is overall review of basic computer architecture, and we will continue with the part on more fundamentals of GPU architectures, how GPU architectures and their execution differ from traditional computer architectures. Now, one thing that is to be very important in this case is this idea of instruction level parallelism, because we will see that GPUs essentially are designed with the basic philosophy that large number of operations have to be carried on by the processor. Now, even at this level there are different philosophies of computing, like how really large number of operations can be carried out. Will it be carried out by executing different instructions in parallel, or will it be carried out by executing an instruction over multiple points, data points in parallel? and among those philosophies, which is the one that is used for GPU. These are the topics from which we will get on with the next part of the lecture, where we delve more deeper into GPU architectures. Thank you.